start. Okay, so we talked about the reduction. In the alcohol chapter, this is kind of nice here because in the alcohol chapter, we did the oxidation of the alcohol, and we made the aldehyde, and we made the carboxylic acid, right? And at that point then, we're just doing the opposite. So all of these are going to go together. And your next chapter is further oxidation of that alcohol or that aldehyde up to the carboxylic acid. So they're all related here. If I take an alcohol, in fact, I'm going to skip back here just a little bit so we can come right to that first page. Maybe not. Oh, well, that's a lot of... Yeah, I don't want to go over that. All right, let's just go to here. Okay, if I take an alcohol and I oxidize it with those chromates, I get an aldehyde, and if I oxidize it more, I get the carboxylic acid. So we started out on the alcohol chapter, and we went this way, oxidized it to the aldehyde, and then oxidized it to the carboxylic acid. Now we're at the aldehyde and ketone chapter, okay? So from a primary alcohol, we oxidize in to get the aldehyde, but if this was an R group, this would be a secondary alcohol, and we would oxidize in to get the ketone. Now the next thing is to take the aldehyde next week, and we'll oxidize it even further to the carboxylic acid. Or we can take the alcohol and oxidize it to the carboxylic acid. So all of this is really, which is nice, just one big chapter. And it all interrelates, which is really kind of how we like to do it. But that said, we're going to tackle the hardest part of this today, and that's going to be the ketal formation. So we also talked about yesterday that in order to attack this carbon, which is, somewhat electron poor, or a Lewis acid, we use a Lewis base of a hydride, and we said, how do we get a hydride? Well, we would add it to a boron or an aluminum, because hydrogen is more electronegative. If I put a hydrogen on a boron or on an aluminum, it would be more electronegative. It would carry the electron. Right? Does that make sense? And so that's where the NABH, and I don't know if your book is going to show you that, but NABH4, does your book show you NABH4, or does it just give you quotations of an H minus? But it really is NABH4 or NaAlH4. And so we'll use those in recitation and the H minus both, so that, whichever way an ACS exam has it, you end up getting it there. Now, also it's kind of interesting to note, because this is really where we're going to go today. Your sugars, when they're inside your body, can reach back and attack themselves. In other words, if you look at 4 carbons, cyclobutane, that was strained, right? Was very reactive, hard to make. If you look at 5 carbons, cyclopentane or cyclohexane, cyclohexane was the most stable. That's because it just seems to be like 1, 2, 3, 4, 5, 6, come back and can touch themselves. So 6 carbons away can bend back over and reach out and touch themselves, especially if there is a need or some type of, this is a Lewis base, right? And this is a Lewis acid. So the lone pairs on here, as they reach around and they rotate and they spin, because they're free to spin, they're single bonds. When this comes into close contact, this Lewis base with this Lewis acid, it reacts. It reacts. These electrons come in and attack that positive carbonyl. And why is this carbonyl positive? Whoops, where did it? Because the oxygen is pulling electrons away from it. So this is another example of a Lewis base, Lewis acid. If the 2 electrons come in, these 2 electrons go out and onto the oxygen, it picks up a proton, it forms an alcohol. So we've kind of reduced this a little bit into terms of now we're at an alcohol. So what happens here is if we take NABH4 and we can reduce this carbonyl, we turn this into these fake sugars for diabetics. That's your little field trip of the day. And so you need to be really careful about these fake sugars. Everybody should, as a not a homework assignment, but a little giggle in your day, go to Amazon and look up Haribo sugar-free gummy bears. Okay? Read the reviews. There's probably 300 of them. And I'm just going to tell you, when I first became a diabetic, I went, okay, how do you get to be a diabetic? I eat too much sugar. I'm addicted to sugar and calories and carbohydrates. So I started using these fake sugar things, and some of them are okay. The rest of them are just a living hell of don't leave 2 feet from the bathroom. But when you read these, I want you to know personally that is so true, and they are hilarious. So you have to be careful, because a lot of these are laxatives, and I'm not talking about overnight laxatives. We're talking about 30-minute laxatives. So I have a daughter that is very critical. It's just her personality. So she would always come in, well, if you weren't such an idiot and eat so dang much candy, if you were always healthy, Dad, you wouldn't have to do these. Are they good? You betcha, honey. They're really good. Take them all and share them with everybody. She lives in St. George. She got to Black Ridge, and they all jumped out of the car and was searching for the toilet paper, because those things are so true. You need to read that. So you have to be very careful about these new things that we as synthetic chemists come up with. The maltose is a baby laxative. Sorbitol seems to be okay to some extent, but for some people, that normoflora, it might just set them off. But there's a variety. The xylitol is in some of your gums. Anything sugar-free, go ahead and look at it. What they've done is they've taken a sugar, and they realize that the sugar, part of this is what goes through metabolism. But if I can reduce it, it will metabolize a different way. But even reducing it still gives the majority of the molecule that same structure that touches the sweet taste buds in your mouth. So it gives you that sensation of being sweet. And at that point, all right, it does taste good. Trust me. You don't know until you eat 10 of them. And then you're in a whole lot of trouble. So we are reducing, but also, I think it's important to note that we're attacking a carbonyl group with an alcohol. So we're still in this alcohol chapter, the alcohol, aldehyde, ketone, carboxylic acid chapter, all interrelate, which is why we put them all together, because you're just rolling in, out, and around. So the next thing is, I believe the hardest part of this.
That molecule, the glucose there. Since it's single bonds, why does it matter that we're showing chunking low different directions? Can't it just spin anyway?
Up here, yeah. So here's what happens: is in your body, and what we're going to learn is you have sugars that have a specific configuration about this carbon. Okay, and this carbon is, we're going to call it a D or an L. It's going to be like R and S. They're going to teach you a little bit of stereochemistry. So how things reach out into space is how they bind into specific receptors. And so the configuration here is very important in terms of your body being able to eat it. And so yes, it's free to move, but around these carbons, the carbons move, but that spatial arrangement of wedge and dash never changes. But even on the open chain, yeah. So when you get there, what I would say is we wouldn't have you do this in this class, but you could go through and analyze each one of these and determine its exact three-dimensional configuration. Its R and S form is what we will do. And it's that binds specifically into the receptor. And so if they were like, if this wedge was a dash, then all of a sudden it would it wouldn't fit, and the whole thing wouldn't fit in it. And so these stereo sensors are very important, and it does open up in some enzymes and close up in others. So it exists in this two forms, but all of these hydrogens and stuff, so on and so forth, stay exactly the same. And so you can build a model set and put those, and so when we get to the amino acids, they're also a unique singular conformation. So the D sugars we eat, the L sugars we don't. but the L amino acids we can use and the D amino acids we don't. So you are a chiral entity. You are a 3D specimen that will only metabolize specific things. And the body requires some enzyme for storage form. We close these up. For glycogen that gets in your liver, if you have branch diseases and you get a fatty liver, it's because these are branching out and you're not metabolizing them as quickly as you should. And over time, your liver enlarges. A few things like that. So what we're going to look at is exactly this right here. A carbonyl, this guy coming in, and because, you know, this is the electron poor carbon with the carbonyl, and this is the electron rich of the alcohol, as they swing around, they do come right into close contact. It can make a 6-membered ring or a 5-membered ring, and inside your body, the enzyme is responsible for that. For your DNA, we turn it into a 5-membered ring. It's that furanose form that we've memorized. Into foodstuffs, we turn it into the 6-membered ring, which is that 6-membered pyranose form. And that's how they all relate together. So the hardest reaction, I think, in this whole chapter and in this test is this ketals, this hemiketal and full-blown acetal. And so we're using aldehydes. So this reaction that aldehydes and ketones undergo, the books in the last 4 to 5 years have changed their names. If we underwent this reaction with an aldehyde, we called it an acetal. If we underwent this reaction with a ketone, we called it a ketal. Now the books, even in all classes, they've just decided, let's just call these acetals no matter what they are. So we have a full-blown, we're going to look at a full-blown addition reaction to get an acetal. The first step will be a half acetal. A half acetal. Say that slowly and pronounce it really good. You can't just say, what did you do today? Oh, we did a bunch of half acetal stuff. So a half of this reaction is a half acetal. Hemi means half. Hemisphere is half. And so when we're half, it's a hemiacetal. When we're full, it's a full-blown acetal. And I will give you a way whereby, when we just went through the field trip, field trip time. And so at this point, yes, what happens is I take my carbonyl, and somewhere else on the molecule, or the alcohol, I ended up being bound, right? So this Lewis base part attacks the Lewis acid part, and therefore that puts electrons up to here, so this picks that up. I'm going to go back to this a little bit, because we already did the, this is what you're made of field trip, but this is what's happening here, and I'm going to do this. Here we go. So this base part, the Lewis base part is attacking the Lewis acid part of this, and when it already has an octet, so when 2 electrons come up, these 2 electrons pick up this hydrogen. And so that's how you make this alcohol. Okay? Does everybody see that? All right. So that's in essence what we're going to do. And so the bottom line is anything with a lone pair will donate to something that needs those electrons. And so this is a general form. It's really just one big mechanism that you don't have to worry about. We could bring a nitrogen in here, and it would tack, and this would be a nitrogen and make an alcohol. We could bring a sulfur in here, and it would attack and make an alcohol. We could bring a phosphorus in here, and it would attack and make an alcohol. And we're going to bring an alcohol in here, and it will attack and make an alcohol. But that alcohol that we brought in will make an ether. And so there's a lot of reactions that utilize this, and so there is one mechanism to rule all of them, but the hemiacetal is the one that is most important in terms of your body. So these are all of the negative charges that we could bring into a carbonyl and end up kicking it out and protonating it and making a product. And your book's not going to give you all of these, but we are going to do the hemiacetal. And it is multiple steps, which is nice. All we have to do is do that memorization. But I do want you to understand, you know, this is where this comes from and why. So here's a bunch of just different groups that have lone pairs of electrons. You'll note that they're oxygens, nitrogens. Oh, what kind of bond is a carbon to a magnesium? It's an ionic bond, so that's a carbon with an charge, right? That's a carbon with a lone pair. So all of these have lone pairs of electrons on them, including these carbon compounds. And then here's that lithium aluminum hydride and the sodium borohydride that we already looked at, and that was a hydrogen with a lone pair. So all of these things have a lone pair on it, whether it's a nitrogen or a sulfur. Sulfur is below oxygen, so it looks like oxygen in phosphorus. Is below nitrogen, so it behaves like a nitrogen. When you go down the period, they behave the same. So all of these reactions, if you understood that, you could predict the product. That just means, here's what my product would look like. My Lewis base would come in, attack the carbonyl, I would get an O-, I would end up protonating that, and I would end up with every one of these things. Now, we don't have to worry about that, but in the H-, if we took an H- here, made this the H-, that H- converted our aldehyde into NaBH4 or lithium aluminum hydride. Either one of those would convert this aldehyde into that alcohol. Okay, that's the reaction we just looked at. So it's an overall general mechanism that allows you to predict everything. I would leave this in my book of, this slide. I actually would probably download all these slides and make me an ACS exam slide, which is the reactions on it. I would put this in here because it's simple enough to recognize that because I'm not after you just doing really good. I think it would be great if you got 100. Because they don't expect that. They make these exams so that nobody gets 100, so that they can separate everybody out. You can still be in the 100 percentile. You can miss probably 4, 5, maybe even 6, and still be in the 100 percentile. But wouldn't it be awesome to just know, I just killed it. I didn't miss a single one. I am more than 100. I'm 1 better, 2 better, 3 better. That's like me having a guitar amp that goes to 11 instead of just 10. Why does it go to 11? Because it's 1 louder. I don't know. So anyway, this would be something I would say just because it's so simple to go, yeah, I got a lone pair, all of these different things would just make all of these different products. All right. Now, back to that at hand, though, here again is kind of the same thing. If I take this chloral here that's almost like an aldehyde, I mean it is an aldehyde, but it's got this dichloride, and I bring water into it, water attacks down here, kicks that out, I protonate this spot, and I end up with chlorohydrate, which are your knockout drops. I told you the story in the dental office, right, where we about killed this poor kid. That's what we used. Good thing we knew our CPR. Man. But here again, comes in, kicks it out, I protonate it with an acid, and I've made an alcohol. But whatever Lewis base I'm bringing in here, which is why I like the term Lewis base, whatever Lewis base I bring in here, I'm still making the alcohol out of all of those. Kind of fun. All right. Here's the Grignard. Nucleophilic additions of things that you might have never seen. Here's a ketone. If I bring this C-, remember this is an ionic bond, so if I bring this C- into here, it comes in, it already has an octet, these electrons kick out and onto this oxygen, and then I protonate it right at the very end. And I end up with that alcohol. Over and over and over again. It might look like it's a ton of reactions, but it's really the same thing. That's the value of understanding the why of a reaction and not just memorizing a bajillion.
Now, the middle one, between the third and the fourth step, where does the hydrogen come from?
It's going to come from this acid. So at the end of every reaction, we do what's called a workup. Because once this comes in here and I get the O-, The O minus is going to form an ionic bond with the magnesium, like a salt, and this is it. So at the very end, we want the alcohol, we have to add an acid. So hydrochloric acid, hydrobromic acid, any kind of acid, and we do that. And we would do that with all of them.
So we start with the Lewis base.
Yeah, we start with the Lewis base, and we quench the excess of the Lewis base that's there with a little bit of a Lewis acid until it's all water. And then, because these are organic, it's not soluble in the water, and so it separates out, and your product is in one of the phases, not the water phase, it's in the other phase. It makes it easy to separate. People get paid a lot of money, you know, $150,000 a year to just beat this crap up. It's fun. It's what I used to do. It's really kind of fun. So this is one of my favorites. I throw this on here just because we like dry ice. Yeah, you use dry ice to make root beer or to make the witch's cauldron on, you know, at Halloween, all of that. We used to use dry ice as a band. We built this big pyramid and we would have dry ice underneath it and it would fill the room with fog. And so the guitar players could sneak out right in front of you and hit that first real hard rock power chord and jump up, and the fog would come. And if you were really inebriated or something, you could say, oh God! It was just so fun. It's just fun. But dry ice, if you think about it, this has oxygen pulling off of both sides. So this would be a Lewis acid too. And when it comes in here, you would just pick it up and kick it out. And now you're right at that exact same quenching thing, and then you're into the next chapter. And there's nothing more fun than dropping dry ice into something. I mean, if you're going to pretend like you're the witch and want this thing to bubble in a pot, you just as well make something cool out of it. So what's fun to do is take, not propyl, but if you take the butane part of this, butanoic acid is what you puke. It's the smell of puke. It is puke. Yeah. When you eat rancid butter or when you eat too much candy, especially certain flavorings are butyl esters in candy. You eat a lot of that, your acids in your stomach hydrolyze the esters, and so you have the alcohol that gets oxidized to the carboxylic acid, and you have the acid because your stomach is acidic, it protonates that. You just have all this acid, and you get this sour, sick feeling, and because most of your candies, flavorings, and stuff have butane in them, you puke, and that's the smell. There's also some butanoic acid in, I think it's Parmesan cheese. So if you make a pizza sometimes and use some Parmesan cheese, it smells like puke. It's like, ew. So it's just fun stuff to play. But yeah, so this would be what you would see in the next chapter. It's all a reoccurring, same type of thing. All right, now that we know that, we're ready to tackle this, the ugliest reaction I think that we see in the book. Now, I don't want to scare you, because if you look at it in the terms of what we said, I have a carbonyl. I'm just going to take the Lewis base part and attack the Lewis acid part. I'm going to get the O minus. That O minus is going to attack that new Lewis base, is going to attack a new Lewis acid. Then we're ready to understand it and realize that, hey, I don't have to memorize this hemiacetal. So a hemiacetal is like, you know, it is a half acetal. If I take this other one and put another R group on it, it will be a full-blown acetal. Okay? There you have it. When you get older, never mind, I won't even go there. We're nurses. Most of us are going to be nurses. I mean, it makes sense that, well, never mind. I was going to go to hemiroid and a full roid, but we'll just stop